We then have here the amida and the ester, and among themselves are groups that in medical chemistry are called isosteros. Now do not confuse this concept of isosteros or isosterism with the concept of isotopes with the octate. Concept of isobars, for example, it has nothing to do with it then. They are isosteros that have a similar chemical behavior, and that is an important concept. Second question. That you believe which of these two groups is thermodynamically more stable. Perfect. Because the amida is more stable. And it is correct that very well, and so well on the one hand, if we go first to that resonance, that they are mentioning me if it is that it is the point of oxygen, it also has resonance, but let's develop the question to find the answer to this, because these functional groups are going to repeat a lot throughout the course. There are many drugs that have esters and amidas in the structure. The same thing happens below. Then below, we can say, well, but this oxygen has two electronic pairs, and one of them can also make resonance. Then, I am not going to bother you with finding complex resonance structures, but if you remember something basic, a movement, an electronic pair, they understand me, and in this case, there is positive oxygen and positive nitrogen. Then, from the point of view of resonance in it, both cases we are generating two mesomeric resonance structures, that this is called mesomeric forms. And there goes the thing, mesomeric forms, and if in both cases there is contribution, but the amida has as a contributor, that is the way that one of the ways that most contributes to the resonance. Hybrid is this structure that we see here on the right, that is the amida much more in this way than an ester has more tendency to contribute with this structure. Remember that reality is an average of both things at the same time. Okay, then, this link in the case of the amida, and also in the case of an ester in reality, this link asks if we classify the links by length, and that will not work for when we see links with protein, which link is longer, simple, double, or triple perfect. Then we have that in general, a simple link is longer than a double link, and is in turn than a triple link. Then the triple link is the shortest given that it is made up of sp-type hybrids. When one empirically measures the length of the link, it finds that in the case of the amides, this link is shorter than a simple link, but longer than a double link. It is an intermediate length. And now the question is, if both have a resonance, because in this particular, we are going to say that this form is much more contributing than in the chemical words, it is much easier to break an ester than to break an amida, because the amida is more similar to a double link metabolically at a biological level that is super relevant, because it asks the peptidic link is of type ester or type amida. Perfect, not true, and that guarantees the stability of the proteins over time, that they are not going to then the energy of this link is much higher than the energy of the ester. Well, the difference is, and not true. Anthony was saying here, there is a difference in the load. Of course, yes, that supports a positive load better is the atom less electronegative. The electronegativity of nitrogen is 3. The electronegativity of oxygen is 3.5. Then, as a general rule, less electronegative, in this case the nitrogen, supports a positive load better. And that is why this resonance is stronger, because obviously something more electronegative wants to be worth the negative redundancy and not positive. So that would be an explanation. The other thing that I have to take the opportunity to explain right here as these groups are going has to do with that. Do not forget that two things, one in the case of amides, will never protonate. This nitrogen to F7. This is relevant when we do some docking in a workshop in a couple of more sessions. It is tremendously relevant that the state of ionization to F7, you know it, and you cannot trust a simulation in a software. You always have to check it humanly because the programs are wrong at this point, and of course, because when there are many nitrogens, the Picassos are specific and the amides because they do not protonate, because the electronic 100% dislocated by resonance and has a positive load differential. And the other has to do with the disposition of the amide. The amide has what is called a transoidal disposition. To see this comes from the fact that in the amides we always have that there are 6 coplanar atoms. That would be oxygen, carbon, the other atom that is here as part of the are the nitrogen, the proton, and the other atom that forms that other R prime, and the rest. The amides, you will always have a total of 6 coplanar atoms, and the disposition is a fourth transoid type, between whom the disposition is transoid between this hydrogen that is down here and oxygen there. I was missing to place it. Nobody told me anything, but I understand that they visualized it. Thus missing the negative load, so this is neutral, then this disposition is always like that. In the amides you are going to say, and why all this hassle? Well, when we see, for example, something called the halogen bridge, when we have a drug within a protein, it happens many times that the halogen approaches oxygen more than nitrogen, and there comes to mind all this issue of reasoning, and it is that it has a higher density, do better the interaction, a very special interaction that we are going to, well, then that regarding these two functional groups of relevance, and there in the table it says that more or less it says an amide dissolves around 3 atoms, or that there are 2 to 3 atoms. Now, here there are several ranges, if you ask me, in how this is a table with values. On certain averages, the approximation works better when one takes the smallest value. Okay, when one tends to take the smallest values, for example, in the case of alcohol, in case of amide, the approximation is much better, and regarding the groups that do not dissolve much, or the groups that are polar but provide little solubility, it says here 2 carbon. I have to make some particular mention, at least one of them, then the last group are polar groups like the rest, but they do not provide much solubility. However, within all these functional groups that are mentioned here, there is one that is rarely in a drug, which then there is the list, so that you are very well. Then we are going to mark it. And now the question is why? Because there are no drugs with aldehydes. There are a few cases already. For example, the aldosterone hormone. In fact, it owes its name to the two that aldehyde is in a cycle and forms a structure of type miestel. And there are also in the food industry, they occupy some aldehydes not so toxic for flavoring, flavas, because both the aldehydes and the esters, that where the esters were up here, tend to generate pleasant aromas, and well, because the aldehyde rarely is part of the structure of a drug. Exactly, and that is technically it is very electrophilic. Then we are going to show here the following, and we are going to do 2 reactions. Look first. The aldehyde functional group is a functional group that is avoided in medicinal chemistry. The reason is that the aldehydes, unlike the aldehyde cetones that are very similar, are tremendously electrophilic. Then this resonance is a resonance strongly displaced to the way it leaves the positive carbon. And these are, I know that they are things that at some point they have the memory, but the biological application is what I'm interested in. Then the electrophilia of the carbon-carbonylic is much greater in an aldehyde than in a ketone. Then this group, that this carbon case is strongly electrophilic, is high electrophilia. We will always see these two concepts, the concept of electrophilia and the concept of nucleophilia. But in biological systems, call yourself in, for example, the proteins, the carbohydrates, nucleic acids, all of them tend to be nucleophilic systems. In fact, for example, the question that loads to see if they remember, I know that not everyone already has this so fresh, but I am going to try to be the most homogeneous and horizontal in terms of the P. Delivery of contents that net load has the positive or negative DNA exactly because of the phi chain of phosphate groups. Then we have that the DNA being negative is nucleophilic. An aldehyde will leave the broom when a protein is joined, genetic material when it alters chains of carbohydrates. Also then the aldehydes react what kind of reaction we are going. There I am going to place a single example so that the point is reinforced in a concrete way. Let's suppose we have the following. An amino acid that has a long chain that ends in amino group. That is positive physiological after this amino acid could be the lysine amino acid, a letter code, which is not the L. The L is leucine. This half rare does not have anything to do with it. Is case. If it is difficult to remember, its codes of a letter all. Okay then, the lysine for the chain is not so short, a long residual chain, and the rest is the amino acid we are going to stop acids. It turns out that from the point of view it has been base, this is positive to physiological pH. Remember that the chemical reactivity depends on who one places in front, then when. An aldehyde is approached here, there is a base acid equilibrium. There is a proton exchange at some moment within the multiple possible equilibrius. And because of that, the lysine can now attack an aldehyde that is superactivated by protonation. Therefore, in the second step of this reaction, mechanism between a protein and the aldehyde, occurs the nucleophilic attack. That is always a nucleophilic amino acid like lysine. You would say, well, what other nucleophilic amino acids? So well, amino acids that tend to react with electrophilic substances that are pharmaceutical or good in this case something toxic are the lysine. I am going to leave here a small list is the serine is the cysteine, and they think of any more. What happens is that the proline, the chain, is a carbon that is cycled in a cycle already does not have an extra nucleophilic group. There is another that has hydroxylo, which is the tyrosine. These are the most common, and that within the nucleophilic groups. So of relevance, these are important because they have chains with nucleophilic groups. And there, if you do not remember very well, you are going to make your way to the walk that you this well. What happens next as a result of this nucleophilic attack? We are going. The lysine is covalently connected to the carbon, and here where's the problem, we start to generate covalent unions, and therefore a protein that has something covalently connected. What happens with its biological properties? Are they kept the same or are they disturbed? Of course, yeah, because it already has something exogenous united and not by electrostatic directly linked with a covalent link. So if that lysine, let's assume that it is a key lysine in a place of a receptor in a catalytic cavity of an enzyme by sticking covalently, that the protein ruins its activity and then below, and this mechanism will serve to understand several others that are going to appear. When one has structures of this type, you always have to remember that it is in the middle of a pit, and therefore, in the middle of a pit, there are many possible acid-base equilibria. I illustrate all, but at some point, instead of being like this, the nitrogen could be deprotonated, and the hydroxyl could be protonated then within the multiple acid-base equilibria. That there are the equilibria of proton transfer are very common. Proton transfer. Well, we are going to have then R and a hat. And here we formed an intramolecular water molecule, and we have our R, and we have our proton. Then I insist there is already a lot of possible equilibria, but this one is formation of the covalently linked product that I am going to tell you what it is called. And now, what can happen whenever you have an intramolecular water molecule that is a very good group coming out of the structure because it is stable, then that water molecule can come out with a neutral load. Then there are two reasons why taking water from a molecule is favorable. I am going to leave it noted here on the right, the water is an excellent. Okay, it is a good outgoing group, One of the first reasons why it is a good outgoing group, because it is a group that comes out, it remains with neutral load, final load, 0. The second reason is thermodynamic, and it has to. Z, when the water comes out, increases the entropy of the medium, increases the entropy of the medium. Entropy is abbreviated as a letter S, not to be confused with sulfur, and so that increases the entropy that we already know that in a very general way it is not the same, but in a very general way it is associated with the degree of disorder a water molecule comes out, and the water molecule is going to come out in this way. The electronic of no link nitrogen expels it by the formation of a double link. Well, this is irreversible here for a pure side, and we are left like this. And here another functional group was formed that you have to know, and this is with a proton, and it has a positive charge, this nitrogen, the certain expulsor, then it is positive, and we have here a proton. And the water molecule that was expelled already asks what is the name of this functional group. To the caretaker, the nitro, that we are also going to see it, is going to appear also quite a lot, the nitro. It is with no two, with two oxygens. This is a nitrogen that looks like a mine, but has a double link. When that happens, that group is a mine, and it happens that at the biological level, there are enzymes, not all. The enzymes in reactions of the electrophilic nucleophile type, cofactors that also oxidize or reduce, and there are reductases that transform this into an amine. So up to here, we have the formation of the amine. What? At the biological level, many biochemical texts call the formation of Schiff bases. If they inject hydrogen, I am going to make a final comment on that. Then we have that there are reductase enzymes. That make this stay fixed forever, because what happens is that an amine turns out that if an amine is a long time in an acidic medium, all this that you see here turn over and the protein would be saved. But what happens is that see this as an anomaly and boom, They inject hydrogen, so to speak, and it ends into an rented amine. Then the problem is that from there it does not return more. Then we would have H2R. We have the rent of the protein in the same way if this happens at the level of O. Genetic material. The genetic material would be rented, that is, the rent of biomolecules. It is a tremendously toxic process, so that is why strong electrophilics are avoided, and there I have to make some comments about it first. I have to give a list of electrophilics, but also, what is an oxidation and reduction? Because we are not going to be calculating states of oxidation. As at some point, it is not true. They did in the past in general courses. We are going to say that in general terms at the biological level, when a molecule is oxidized or reduced, an oxidation at the molecular level consists of increasing the amount of oxygen and or reducing the hydrogen in it. The chemical structure, vice versa, a reduction is a process that increases the amount of hydrogen or the amount of oxygen is reduced within the structure, whether it is a drug or a biomolecule that increased hydrogen, and or because it can happen in parallel in both things and ID protons, that is an oxidation, increased hydrogen or reduces oxygen, that is a reduction. And so I am not going to be asking you about oxidation states and things like that, concept that allows us to explain biomolecules, and on the other hand, and the question is, will it be the only electrophilic group that is delicate and who cannot have it in E? Drugs? No, we are going to give here a small list of strong electrophilics that one avoids when designing biomolecules. Then in the end, in that global test that you are going to give, you select some things, and strong electrophilics must be avoided as the following. Well, we already saw that the aldehyde that is abbreviated, so it has been taken to avoid it. Second, derivatives of highly reactive carbon dioxide, such as aluric acid, one very common. An acid chloride, also in that position where the chlorine is. It is common that there is also a joke. Question and a iodine. Connect iodine because what happens is that this carbon-carbonylic halogen bond is super weak, and this is easy to break by a nucleophile that attacks here, similar to what happened to the aldehyde. A nucleophile can attack this carbon, and the protein is acetylated AI to place here because it is very large and the covalent bond becomes very unstable. Okay, and then 3/3 electrophilic question occurs to you. Some others. Remember some of the past. Some other electrophilic apart? Yes, of course, because we make reactions with this as it is already to form the amides or any other system. Well, another electrophilic group are mostly carbon dioxide derivatives, the anhydride. That is like because in the anhydride one of the halves behaves as if it were an halogen. And for example, arbitrarily as there is the right half that is as fragment were a good outgoing group of the structure in this particular case, an halogen. So also the anhydrides are very unstable, highly reactive, and can acetylate protein. The acetylation of a protein again alters it because it is covalently linked. To see it is not the same, this concept is different already. This functional group, the anhydride, is all. This to see, and all this group is the functional anhydride group. Is the name of the functional group of a molecule in specific, and I think that there are the most relevant I am trying to remember, or if you come to mind some you can. Tell me, but I'm trying to remember if there is any other that is also toxic, that is looking. To avoid in general now, there are other groups that are stable, but that are occupied the same because, due to that toxicity, they serve, for example, as antitumorals, they are cytotoxic. So I think that these three are the most relevant of all the groups later. I could mention them, and then those that are cytotoxic for a chemical issue, the same selective. No, there is the problem. If that problem is not very selective, for example, another strong, but not by rent, I am going to write it in another color, so that later it is not they are studying. It is the nitro group. The nitro group is not that it rents or acetylates a protein. The nitro group within the cells generates free radicals, of course. Then, when the cell in the mitochondria begins to metabolize the nitro group to make it more soluble, because all metabolism points to that, when there is a rare exogenous, the metabolism tries to take the molecule to make it more soluble, and so that it can be excreted. Then when that happens, they are generated in free radicals, means okay. Nitro group owes its toxicity to that, and that is why the nitro drugs to kill bacteria okay within a family called the nitro and midazoles serve to kill bacteria due to that toxicity, but that implies that they also cause damage to healthy cells. And of course in degrading it by oxidation very well. And talking about bacteria, recently, the feed. Colleague in the morning told me up there that in Argentina, many people have died from a bacteria. I have not seen the news. It seems that it was not by a left. What it was, a fentanyl, I think. People who were injected fentanyl, which is a strong drug, a narcotic, and the problem is the vials were contaminated with a resistant bacteria. They say that about 100 people have died. Imagine then, the issue is drastic already. Well, it would be these four functional groups. I think it is worth mentioning them. We go back to the point with that we already finished apart from the nitro. Apart from the nitro apart. The nitro, if there are several more, and they are more complex. For example, we on the margin, but this group is occupied okay. That is all this piece of molecule like this with this way. And of course, this is a quinone also, but it turns out that all this organic fragment, because here we already have carbons, and they are occupied in the formulation of other drugs in more complex structures. So it has practical use despite the fact that the parsley is half toxic. The cancer they are studied for malaria, so due precisely to that toxicity, they have to generate oxidative. And we already mentioned that of the membranes, and now I'm interested in going to the one of logP, that you can read this little by little, but I'm interested in getting to the other. The exercises are all ready, as we are going to have to see this too, since it has to do with the fictive Henderson equation that we are going to explain it. I am going to refresh the memory in a little while more, and I am still not interested in going to the functional groups. And then let's see. And it says which of the two presents greater solubility, first in the compound that is here on the cocktail. Right, and this structural pattern that we have here to see this is not has a drawing there very harmonic that we say, look, if we draw it in a more professional way, it would be like this. Then we are going to take the pencil here and we draw the connection in this way. This is like this. So, how many chiral carbons does this system have? Very well, it has two chiral carbons. Then how many possible stereoisomers exist? Of course, the possible stereoisomers is 2 raised to n, where n is the amount of chiral centers. Therefore, in this case, it would be 2 raised to 2. That is 4 possible stereoisomers with this type of structure, and when I mention this is part of the matter, and sometimes the information is perhaps not so systematized, so as not to make it so boring, but they're together. Certain pharmacophores at the end of the course, what interests me is that they take their memory in the long term as many pharmacophores as possible, because that will allow you to read information in the future when you see a chemical structure. Benzenitate is phenylethylamine, that we are going to that name because it is relevant to phenylethylamine. That sounds to you or not? Phenylethylamine, any idea? Which sorry phenyl already look, it resembles the name of several things that you may have. Heard that are sold in pharmacy, stimulant molecules, suppressors of appetite, of course. If this type of structure are stimulants of the central nervous system, phenylethyl here. There are 2 carbons, there is 1 extra, but in the main chain, there are 2 amine phenylethyl. Then notice that I do not mark the hydroxyl as the most relevant, and the amine is pharmacophore, because this has a stimulating activity. It is used as a stimulant. Let's say as a drug, although it could be misused as a drug, but this is a stimulant for the following, maybe this molecule if they know it. And here I am missing this and this from here. This is a neurotransmitter. Very well. Excellent. It is already a neurotransmitter. Well, no, but that's where the thing goes. Look at this. That is here. With the free methyl is norepinephrine or noradrenaline. It is this. And look. And if they put a methyl there, it is the adrenaline hormone or epinephrine. It is the same. Adrenaline is a non-hormone. Noradrenaline is a neurotransmitter, and NT. Noradrenaline is without the methyl. Adrenaline is with the methyl, only a methyl of different similar biological properties, because the molecule are very similar to each other. Then question at the conceptual biological level, what is the field difference between saying neurotransmitter and saying hormone? Very well, perfect, excellent. This is short range, and neurotransmitter occurs in the release in the synapses. Very well. There it acts to communicate neurons. The other is released to the blood plasma and has an effect on several organs at a distance traveling through the blood stream. Very well, perfect. Then, when one sees now the comparison of this molecule with this molecule, that is here, one says, then now, yes, now I understand why the pseudoephedrine. Now the pseudoephedrine has a stimulating effect at the brain level because it is similar to norepinephrine. It has the pharmacophore. Remember that concept, it has the same pharmacophore. And where have you seen the pseudoephedrine? In the antifreeze. Very well. In the antifreeze, it is common that one observes paracetamol 500 milligrams, which is an analgesic, to calm a little the headache, the pseudoephedrine. In a lower dose, 60 milligrams, to act as a nasal decongestant and stimulant. Also, from the soul, a little, but the effect of nasal decongestant is one of the most powerful, because this is a constrictor glass, the pseudoephedrine, as well as the adrenaline is a constrictor glass. And what else? And chlorphenamine? Chlorphenamine? 4000, clearly that is the antihistaminic, to cut the secretion. Okay, to cut the release of histamine and that other issue, the chlorphenamine. Not the chlorphenamine, what it does is act as an antagonist of the histamine receptors and in E. That way, it prevents the release of more histamine. Okay. It is an antihistaminic. It is a blocker of all. The effect of the histamine, all that has its pros and cons, you know, because when one is cold, of course, histamine is released, which produces edema, redness, nasal secretion. But all that has a reason to be is so that it increases the vascular permeability of the capillaries, and the white blood cells can more easily cross to the site of already. Ask which of the two, by instinct, based on everything we have seen, is more soluble. There is the question, which will have greater solubility? Exactly, very well. In fact, we could calculate, because we had said that on the lower part 3, atoms are not true then. For example, here I have 1, 2, 3. This has 678. So yes, that is why it is soluble in water. And this other also, because all that one here we have 6,789. Here it does not reach it. It is not true, because it would be 6 atoms. And if the nitrogen is protonated in the form of salt, it in one, so it does not have complete solubility in water. Okay. And this has a pauperimous solubility. That is here, that it is the menthol that has 6,789, 6,789, 10. Then the menthol that is there asked, is an alkaloid or a terpene? An amino group to be an alkaloid, of course. And since it does not have it, it is a terpene. But we have to define that it is a terpene, because not because something does not have nitrogen, necessarily it is terpene. It could even be an artificial molecule. It is an extract not true present in several aromatic plants, and we have that this menthol, if you count good first if there is no nitrogen, but if you count the carbons, it is multiplied. It has 7, 8, 9, 10 carbons. When something is multiple of 5, we suspect that it is a terpene because it comes from the metabolism of the isoprene, which is the simplest structural nucleus, from which terpenes can be synthesized. Okay, and the isoprene has the following chemical structure. 1, 2, 3, 4, 5. There it is. It has 5 carbon atoms. Okay. Then any molecule that comes from the metabolism of the isoprene will have a multiple of 5 carbon atoms, and that, technically speaking, is a terpene. That is, it is a second metabolite, but it does not have nitrogen in the structure. Interesting. Then they already have the rationalization of the 2 large groups of natural compounds, secondary metabolite. Alkaloids and terpenes, they already had the definition, and they have concrete example already solved question. Let's go to the next one, and look, you know that one more thing here. Notice that in the case of adrenaline or noradrenaline, intentionally, the hydroxyl group, I drew it forward, and it is that it has that configuration. That configuration would be that because this is also going to seem a lot to us. This carbon is R or S. Very well. 1, 2, of course, exactly. And then it comes here to carbon, or in the distance it is already very far away. And then remember the rules. If they were called assignment, this is a carbon of configuration R, and what happens if it were? The human metabolism is an anti-homatically selective. The molecules are always created with R. Define chiral centers in an absolute way. If this were that, the bioactivity is lost, or considerably lower. We are going to the second problem. And it says, well, identify functional groups and what is its basic acid character and which increases its solubility in water. We are going there first from the point of view of the functional groups. We have that in the first drug called timolol, which is a beta blocker agent. Look. What happens here? This is a beta blocker we have that the ring that you see here, I am going to upload or send at some point a small list of heterocycles that we have to know for effect of this course. This ring is an uncle of Sun because it has two nitrogens and it has a sulfur. And second, this ring is or is not aromatic. That is, it has electronic aromaticity if it has. And because, what is it that? Exactly a pair because it has two pairs of electronics, but one of them integrates it to the resonance. Then what I am asking you there to remember is what is known as the rules of electronic aromaticity. So that a compound has aromaticity, that is a type of orbital conjugation, and therefore is a type of molecular stability. The aromatic rings are super stable. One has to be fulfilled that obviously the compound is cyclical too. The compound must be flat now, you will say. And how do we know if that ring is flat as a general rule? The rings that have more than 8 atoms in the structure are not flat. That is, if you find a monocycle of 8 or more, they, or more, twist in space, but up to 8, 7, they already endure 8, and the probability that it deforms is very high. So less than 8, they are flat when they are monocycles. You can have several pegados. If I can have several pegados and they are flat, okay. But there we are talking about. And the third characteristic must have how many electrons conjugated. 2, or there was a formula for that. There was a formula like that, and what was that formula? Okay, let's go there. There was a small formula. If I am going to check the case a little there, yes. This is important. They must have 4n plus 2 electrons conjugated with n equal to whole, including 0, 0, 1, 2, etc. N must be a whole that. Number of electrons conjugated must comply with that mathematical requirement, and if that is fulfilled, all the p-type electrons are linked together, so we have that here in this ring, if you count, we would have 2 here, 2 here, and only 1 participate. An electronic pair of the sulfur, then there, yes, only 1 electronic pair of the sulfur participate. We therefore have 6 electrons, 2, 4, 6, 6, complies, with 4n plus 2. Yes, exact then, if it complies, it is an aromatic ring, and only the sulfur incorporates a pair. Then it is an aromatic ring, and if it is aromatic, it is flat, and if it is similar to benzene in electronic properties, it will have a certain resemblance, because benzene is aromatic too. And then now you say benzene, we just follow me here because I want you to go in and read the structure that we have now. This would be aryl oxy because there is an oxygen in between aryl oxy, and now we have more carbon, yes, propanol. Because here there are 3 carbon amine, then you say it looks like what we saw above it is not true, that it was phenylethylamine. It was a little shorter. This is a little longer. It is aryl oxypropanol amine, but it looks like it is not true. Then look at the conclusion when one has this structure like this, and here I introduce this new concept, and this is not true phenyl. Etylamine here is the natural molecule phenylethylamine. When we have this type of pattern, this type of molecules are agonists adrenergic. Agonists, stimulants of the adrenaline receptors, of which there are several subtypes. There are the receptors of type alpha, within which there are structures that are GPCR, and there are also other structures, if I am not mistaken. I think there was an ionic channel, or not, the serotonin. Then we have that there are receptors of type alpha of energy and receptors of energy. Okay, and there are several subtypes also, and these are agonists. But if you have that oxygen there disturbing, so to speak, and also another detail, a large group here at the end, that would be this, as it is chemically iso or terbutyl is a terbutyl group because it has 4, 1, 2, 3, and the one that is here is a 4th. Carbon, it is a terbutyl group then, when we have these things that disturb the structure. This oxygen and this large group, now this type of pharmacophore called aryl oxypropanol amine. This is an aryl oxypropanol amine that is an agonist adrenergic, the opposite. Agonist adrenergic. And there I am going to give you some tool so that you can reason with this. An antagonist looks like an agonist, that is. We just saw that there is a certain resemblance, and it makes sense because if I want to link myself to the same receptor, that the agonist I have to look a bit like it is not true. But what is the difference? The antagonists ask. They are more or less united in the cavity of the receptor. What do you think? The antagonists are more united, more time. That is why this group generates more hydrophobic interactions. Increasing extra group here is so that this is held longer in the cavity, and it look then the antagonists have a longer permanence time in the cavity. The antagonists, then they have a longer permanence time in the cavity. Yes. No. Of course, sometimes there is also an allosteric antagonism. There are negative allosteric modulators, so we are also going to give concrete examples of that. So, yes, thanks. Exactly, and there they occupy it. Of course, they are different, so it is very good. And then look, we are going to do the following. To see, I am going to insert a page. Because the agonist is M0883, and the other is the antagonist, and the cavities are different, of course. If you can, it can be given now when you see similar structures. Remember that sometimes the three-dimensional geometry is not necessarily the same. Well, move the page. There it is. We already have these three concepts that I also take advantage of defining now. The concept of agonist, the concept of antagonist, and the concept of inverse agonist. That I could define both in a pharmacological way when one studies what is called curve of dose and response. But as we have not yet reached the pharmacology course, so we are going to define it in the following way: all the receptors up to where it is known they have a certain constitutive activity. Then if one draws, for example, here, a receptor, I already have a receptor, and this receptor is going to have a certain constitutive activity. That is, when I say constitutive activity, I mean that the receptor there is signaling that is called the constitutive activity of the receptor. Analogy, and because I know that sometimes it is difficult to assimilate this concept when you have a radio on a very low volume. That is how that noise is true. That little noise receptor, in the absence of the endogenous ligand arriving, said receptor is signaling intracellularly. And the radio turned on to a low volume now asks, what happens is how can you signal if the agonist has not arrived to stimulate it? Because the agonist, that is what an agonist does. Okay, the agonist then. Linking the agonist well. One can open it with LL linking is a general term in medical chemistry for any molecule that joins some protein well when theta agonist. What happens is that when it joins there is very well and the activity of the receptor is fired. Only what the agonist does is stimulate. But how is it that the receptor is in the absence of the absent ligand? Whether the agonist or the endogenous ligand, how does it signal well? We have to remember that this is not in the void. This is anchored, for example, a membrane, and asks the cell membrane is a rigid system or a fluid system. Very well, then we have that. As the membrane is a fluid system, it is a system that can mechanically generate alterations in the structure of the protein, making that base signaling is maintained. Okay then, that arcane vision that this is like a fixed medium is not like that. The membrane itself is almost like an extra organelle of the cell, and the membrane is alive, so to speak, generating conformational changes in the receptors, and the membrane can make this basal signaling remain. We go to the other side. When we have the antagonist in the same situation, we have our receptor. And our receptor has the constitutive activity, and what the antagonist does is join and stay together for a long time. That is, we have that it is a union of high permanence time. It tends to be like this. It is no longer an absolute law, but it tends to be like this, that the antagonists have many intermolecular interactions with graph strong. They are going to move all the intermolecular interactions. And for example, the hydrogen bridge is the most common in a certain way, a lot of so to speak, and but when the antagonist joins and blocks, the constitutive activity is not blocked. Then there is no blocking of the constitutive activity of the receptor. Okay, the constitutive activity remains. It is raining. I did not come very prepared. We say I always have with a vest all. Just now, a rare one is in the climate right now. Also, the climate does not come. Well, and finally the last case, the inverse agonists, is when the ligand arrives. Then it joins here to the cavity and suppresses the constitutive activity. Then it suppresses the constitutive activity. Then it asks the inverse agonist is acting as an agonist or as an antagonist. And as none of the two, but in terms, now macro, that is within the cell, there will be no answer. There will not be then as an extreme antagonist, so the name is used for confusion. Be careful. And another aspect, of course, it would not be true that as if the receptor had several outputs, so to speak. Well, in this case in particular, what it does is suppress the constitutive activity. Receptor, in all these cases, what we are explaining is a behavior of ligand that joins the protein in particular, that joins in a standard way to what is called the orthosteric cavity of the receptor. To differentiate it from the allosteric cavity, that is another thing then, we have that. The ligands join the orthosteric cavity, and we have these three possibilities asked. An endogenous ligand, such as adrenaline, that we were just seeing, or serotonin, that you meant shown to me, or any biological molecule that comes to mind, hormone or neurotransmitter body that are biologically, they are agonists, antagonists, they can be both. They are only agonists, and without being careful, the endogenous ligands only have agonist behavior. That is, they fulfill a conceptually speaking function. They fulfill the function of, now you will say, and how is that? That some generate the blocking of others because for example, if I arrive and I link to a certain receptor, that signaling cascade generates a certain effect. That's so if you can block it to another, they understand me then. The concept of antagonism at the endogenous level does not apply. That is a human creation. The ligands that we have endogenically, conceptually speaking, are of the agonist type OK4K4. Example, when we talk about, I am trying to think of something that comes to mind quickly, the chlorine channels in the brain already. When one thinks, for example, the chlorine channels in the brain. When the GABA neurotransmitter reaches a chlorine channel, when the GABA neurotransmitter arrives. Here the GABA neurotransmitter is linked. The chlorine channel opens OK, and then if the channel opens, it will enter the cell, it will enter more chlorine. That is, the cell becomes more negative inside and more positive outside. Hyperpolarizes, exactly generates a hyperpolarization, and asks, and a hyperpolarization makes the signaling be more fluid, or it is stopped. It is stopped. There we have the effect and the biological effect. The final effect is opposite to what one thinks, that an agonist is like stimulating and things like that. No, because not necessarily. Okay then, the endogenous ligand makes more chlorine enter, therefore conceptual speaking, that it would be an antagonist of GABA. It would be something that blocks this. Chlorine will not enter, and therefore what will happen? We will have neuronal excitement. Oh, that is what is done with people who are drugged, or even sometimes try to commit suicide with diazepam and all these molecules, with benzodiazepines, the diazepam and all the other benzodiazepines. Do this the same as the GABA, they make it between chloro, and that is why they sleep the person. Falls asleep and is drugged with this, or they try to commit suicide, and what is injected is an antagonist GABAergic, so that more chlorine does not. Okay, then having explained these concepts, the last thing that is left for us conceptually to return to the point and hear this. You have seen that we have delivered the concepts in a slightly different way to how a conventional pre-grade class is done. For example, look, taking advantage of the fact that we have this of the orthostatic site, there are also allosteric sites are not the orthosteric site, but they modulate and modulate indirectly to the receptor. Modulate indirectly to the receptor. Then we can have our I am going to do it now in a slightly more graphic way. Let's say that this is the orthostatic site of the receptor, but our receptor also has an allosteric site. Then first, and this is our receptor, we are going to say that then if it is the orthostatic site, square the endogenous ligand is that molecule that has affinity for this site. So here is the L, where L is the endogenous ligand. Then We want the endogenous ligand to be joined, but what we are going to do here is to design a different molecule. We are going to design an allosteric molecule that does not compete with the ligand. Allosteric ligand. The allosteric ligand does not compete with the orthosteric ligand. It links in another cavity, but it generates an indirect modulation, and there may be three possible results. It could happen that the allosteric ligand strengthens the activity of the orthosteric endogenous ligand. I know that this sounds a bit like tongue twister or orthosteric, but the idea is understood. Then in that case, we are going to say that the molecule is called in its acronym in English, PAM, or positive allosteric modulator. Then what is the requirement? The requirement is that the endogenous ligand has to arrive. The allosteric ligand joins and strengthens the effect of the endogenous ligand. How it strengthens it, if that is a protein, is a structure in quotation marks of amino acids. Well, what happens is the following. And if we have time later, I can explain it when see some concrete examples, such as the case of the allosteric modulators of calcium channel. When the allosteric ligand arrives, it generates a change or induces a conformational change of O. This cavity, making this cavity have more affinity for the endogenous ligand. That is, as the cavity tightens more and grabs the endogenous ligand better. That is what happens in the positive allosteric modulator, but the opposite can also happen. When the allosteric ligand joins it, obstacle slows down or blocks the effect of the endogenous ligand. Despite the fact that it joins, it generates a conformational change such that now the signal, and that would be a negative allosteric modulator negative. There is its acronym in English. NAM, negative allosteric modulator. There are two alternatives, and you will say, and that serves for the design of pharmaceuticals. Medicinal chemistry is being used a lot today. It is being sought a lot because it turns out that it is less invasive than creating a molecule that acts on the allosteric site. That more physiological effect is softer, so to speak, so that today it is a tremendous field of exploration, and there is another reason more. And then the first reason, invasive, and the second reason is that the most common membrane receptors, and that are most used for the design of drugs, are those that are known as receptors coupled to G protein, or GPCR. How much GPCR exists? A lot. They already say that there are more than 404 they have not even found. What many of them are used for? There are many who call them orphans who have no idea they are. There they do not know well what they are used for. Then there is another field of research in which you can do a lot in the morning, no? I believe that there is always a possibility that something new is discovered. There is always a possibility that something new is discovered. There is one that is good, for example. There is one that is the GPR55 that is said to be a third cannabinoid receptor, so it could serve for the treatment of addictions, it could serve for cancer, it could serve as a neuromodulator in some epileptic seizures, etc. Which one more? There is another, without wanting to be self-referring, that we are studying with other colleagues in Santiago that is called GPR61, and that has several, for example, in cancer. Then there is a lot that can be done with orphan receptors, whereas when I say orphans, it means that it is not known which is the endogenous ligand, and it is not yet understood very well what its main function is. Sometimes the function is first discovered before the P. Because many times the ligands are like membranes, lipids, molecules that come out themselves that are difficult to detect. For example, that famous receptors have membranes, lipids that stimulate them in the channel of cancer. There is one, and also the cannabinoids. And well, here we have a little, And what is the third? If they come to mind, there is a third option. That is how it is always the neutral effect, as I can no longer use the N again, I am simply going to say neutral austere modulator, and I am going to write here neutral. That is, it does nothing, it only maintains the receptor with the own response that the endogenous ligand will generate. So you could do it. I do not have any example coming to mind, but very good observation. I insist it could be, but there I would have to look for it. I would have to look for a specific example. But very good Christian observation. Maybe it is not true. An effect of some vitamin, and you know. The other, since what could this selenium be used for? Yes, of course, yes. I insist all that. Could be. I would have to look for the operation well there, yes. Place to the austeric for said element, because it does not have to join here, it has to be a different cavity. Now sometimes these cavities are so close, that is true, so that a little more inside the other element or cofactor is joined, so to speak, and look at the other. That I was going to mention is that sometimes in the case, imagine a positive austere modulator there, it would be convenient for us to compete with a neutral or nothing more than to prevent overstimulation. And then we gave the list, and we explained that, and asked to see here, and here I am at. Advancing because we have not yet done mathematical calculations we also need to do, but I advance a little to the contents, seeing the structure that there are several nitrogen atoms, and the nitrogens are bases par excellence, but protonable, which nitrogen is the basic nitrogen of the structure. You will not even go for this, because when you do a docking, you need to know which one will have a positive charge. Interactions with the protein depend on that. So it does not matter mass and the extra proton which is protonated, which is here to see first. This ring that is here is called, what is called this ring is called morpholine, exactly, if this is not protonable, because exactly because it is in resonance with the aromatic ring, strongly dislocated and well. This is not a kind of heterocyclic chemistry, but these systems are called P-deficient systems, and they are tremendously electroattractive. That is, a nitrogen in Cp2 within a ring acts as a carbonyl. It takes electrons away with a lot of force. Okay, then this P-deficient electroattracts with a lot of force. That morpholine is not going to protonate the one here. Okay, then that nitrogen will still have a positive charge to F7, and therefore when they do the docking of this, they will have to put the proton and positive charge there, or check, because sometimes I have seen it has not happened in thesis, that we have seen sometimes docking that, but it did not protonate there. Then all the work comes to the ground, that all the discussion has been good. But if it did not put the proton there, with the most, all the conclusions are wrong. And sometimes programs, as much as I said, the pH give the same. This also generates error that generates as if it is confused. I do not know what happens there with the algorithms that do not protonate it. Also seen it even in paper. We have seen docking of neutral molecules in some articles, so that cannot be perfect. We are going to the last one to finish this before closing the block, and this is called latanoprost. Is a drug used for the treatment of glaucoma like the previous one, but this is for one that you want to see. Look. Question: you believe that these two drugs, timolol and latanoprost, that are used for the treatment of glaucoma, that is for intraocular pressure, exacerbated. What is the problem with that? That a lot of intraocular pressure causes the retina to be damaged, and the person So it is not only a question of pressure, and the problem is that it is silent disease. Look at what happens here. I'm going to move this a little bit there. Seeing the structure here, I am mad. Introducing you to all this basic structural analysis. Do you believe that you are mechanism of action? No, I do not know why this one here does not pharmacophoric aniloxypropanolamine. There is not even a mine here, and which question Latanapros could be a pro-pharmacist, because theoretically it is not an ester boot. It turns out that this is how it is acted, and then means that it is pro-pharmacist, and now I ask the question in another way, easiest metabolic degradation point, and what is going to form there when that breaks? I'm not going to draw the whole molecule, only this little piece. When the ester breaks, it forms a carboxylate, a free carboxylic acid, increases a little the solubility. We already have that here. There is hydroxyl, and total we have a quantity of how many central centers do you here? And let's see, we have 1, 2, 3, 4, and where's the fifth? Exactly there inside the cycle, and what else? There is another element that has to do with stereochemistry, that does not give the same orientation, and that it is fixed. Because the central centers cannot change, they are already fixed in the space. Okay, very well, the double link as it is there, that is fixed, and that is E or Z. And if it is because the chains of greater atomic weight are on the same side, that is why it is called alkano zot, and it is an alkano of configuration Z. Not A-OK. All those things are relevant. If we had the E capable that it does not have activity, or has less the same if we all central centers we lose activity, or it has less, it does not necessarily lose it 100% so. The action mechanism is going to be different question. How do you see the solubility in compound very well super low, but it has too much carbon and few functional groups, the only Lia. Most polar are the hydroxyl, 3 carbon, and 3 carbon, and an ester, that maximum 2 carbon, almost nothing. Perfect, and of course as is, and well that allows it to go through the membranes, and get inside the hazy humor, and the last thing it says, and we identify the functional groups which is more hydrophobic, and we already know that the tanoprop would be more hydroformulate a salt. Well, that would already be implicit here, that in the first one, salt in the amino group very well, and with this we finish for today here again, basically the same we have there, the vitamin C, and the biotin question identify you in some one of them, some acid group. An acid group, that means a group that can release very well in the biotin. That group can release a proton very well, and therefore physiological pH, we are going to have a balanced thing that already in the specific amounts that is an acid group. Okay, question. What is the name of this functional group? That is NH carbonyl NJ. And it is no longer a measure, it is like a double measure, that is urea. And up here there is a sulfur that is also part of another functional group because it is interconnected there with that carbon and that point up there, that sulfur with that. Carbon is a point of metabolic degradation in fact, it is quite simple that some enzyme comes here and breaks there and degrading the vitamin. So what would this group be called? Or what does it look like? It is common. It is like an ester, but it has sulfur, then it is a type of ester. And we have not yet finished answering the question about the issue of acidity. It turns out that there is still another acid group in the structure, which, when they have eaten chewable vitamin C, and how it is acid, then the point is why if they do not have a carboxylic acid, in fact, look at the vitamin C already. Not so much what happens is that, well, that is important. Vitamin C, it degrades. Of course, exactly can be broken here and therefore it loses activity, but it is acid, and that acid flavor that you feel is because it releases protons, and that release, well, the proton that is released is from some of these hydroxyls, and for there with that we actually end today, these that are here are neutral hydroxyls, and I advance to the concept with which we go deeper into the next block, and they have pK sub A16. Do not that the next class we are also going to do calculations with that, and I am going to explain it in two hydroxyls, and that is, they do not release the proton, never not true, but look here how it is called a double bond with alcohol. This is an enol. They are two enols or double enol as they want to call it, because it is a double bond that has hydroxyl and hydroxyl, and it turns out that of the two, one of them is. More is more acid. The question is, which is more acid? The answer is the one that stabilizes the negative. That is, when the proton is released, the one that is more acid is this one here because it stabilizes the negative charge better. I explain with this. We are finishing when the negative charge is formed here, because it stabilizes it better as such by the double bond, by the conjugation, because it has very well, it has a perfect resonance up there, and that explains why that is the hydroxyl acid and the acid flavor that you feel for the release of that proton as such. To greater conjugation, that is greater resonance,